Hello everyone, this is Muhammad Nasruddin from Control Systems. I am truly delighted to present this lecture about system identification in control systems. So let's jump to it. This is outline of this lecture. We are going to go through introduction, methods of system identification, types of system models, system identification setup, system identification from a step response, and practical consideration. So, what is system identification? System identification is the process of determining mathematical model of a parameter or a process in a system. And that is basically based on input-output data measurement. So we have this system that we want to identify the mathematical model of this system in order to study or analysis how this system works to design a controller to do certain things or to provide desired response as we do in control systems. There is several steps we take in order to identify a mathematical model using system identification. The first step is to do input-output data acquisition. The second step is to select or estimate model structure. The third one is to estimate the model parameters, and the fourth one is the validation of the identified model. So in the first step, what we do is basically we take our system and we give it input signal, and we measure the output of the system, and we measure set of values through a finite time, and that is data acquisition. After that, we select a model like a transfer function of that system, or we estimate. If we don't have a model, we estimate that model. The third step is basically calculating the parameters of that model. So we need to precisely and accurately define the constants and the parameters that affect the system response and behavior and so on. And the last step is to identify that this model is actually right. There's two types or two methods we're actually going to consider in system identification. It is either online system identification or offline system identification. Now, online system identification is when we identify the system parameters and system models when the system is actually under control and doing its job. So we take recursive data of input and output and determine the model parameters based on that data recursively when the system is under control. Offline system identification, on the other hand, we take our system and we give it a series of input, we observe the output, and based on that input output measurements we can identify the system model. Types of system models. There is two types of system models. System models of control systems, or basically mathematical models, have two types. It is either parametric models or non-parametric models. So what exactly is a parametric model? A parametric model is a model that contain arithmetic parameters or values like a coefficient of differential equation, difference equation, transfer function, or a state space model. It's basically always a mathematical representation of the system. The second type is non-parametric models, which basically is a given representation in a graphical way of how the system behave over time, or over change of frequency, like Bode plot, Nyquist diagram, and so on. So enough theory. Now let's jump to practical. This is a setup of system identification. For example, if I have a system and I want to identify the model of that system, as you can see, we have this system here. It's a black box and we don't know anything about the system. We want to identify it. So what we do is we set our system identification setup as shown in this slide. We take several inputs, we give it to our system and record the output simultaneously while recording the input. The input and the outputs have to be recorded in a synchronized way. Okay, we take the input and the output simultaneously are recorded using a data acquisition, which in this case is this little microcontroller Arduino Uno. And after that, what we do is we take this data and we plug it into computer. If it has a identification toolbox like MATLAB have a nice system identification toolbox to use it in such calculations, or we do our own calculations based on the data we have, system identification from a step response. So in this block diagram we actually have our system and have our setup just like this, and what we do is actually we take our system and give it a step response, and after that we record the system response from the output, and we draw it using computer software like MATLAB, and we end up with something like this. On the left we have the system response from the practical system, and right we have a typical unity step response of a first order system. So by comparison we know that our system is first order, and from that we can calculate the model parameters. We already know that the transfer function of first order system is in the form g of s equal to k over s plus a, where it is the system ball and k is the gain. So by going back to our step response and comparing these two, the typical step response of first order system and the practical step response of our system, we can calculate the constant a. When the response reaches the value of 63% of its final value, we have in the x-axis we have t, which is time, is equal 1 over a. So we do the same thing here. We calculate a, or 1 over a. From here we can say that the response final value is 0.72, roughly is 0.72 here. So what we do is multiply 0.63 by 0.72 and we get roughly about 0.45 or something like here, and from that we can go here and calculate the 1 over a, which is approximately 0.13 or something in this area. And the rise time is the time required for step response to go from 10% to 90%, which is from here to here. So we can take that time, and using this equation t rise, we can calculate a parameter, or the other equation ts is equal 4 over a. We run the clock and basically observe the time until our system comes to settling, which is approximately 5a, 5t, t is the time constant, which is 5 over a, something like here, and we calculate this time, and using the last equation ts equal 4 over a, you can get the value of a. And finally we have to calculate the value of k in the transfer function, and we basically get that from the final value of this system response, because it's actually affected by the gain. If you do the calculations and you block the step response to your system, and you take this transfer function and do the inverse Laplace transform and so on, you will end up with two terms, a forced response and a natural response. And the forced response is actually going to be k over a, so the final value is k over a. And we get back to our graph, and the final value is like 0.72, so 0.72 equal to k over a. We already calculated a and we can calculate k. So that is typically how you do a system identification for a first order system, but it is basically not going to be like that in practical systems, because most systems are two or three orders higher. Most systems in practical actually are second order, third order, or fourth order systems, and so on. And even high order systems can be approximated to second order system. So when we identify the transfer function of second order system, we typically do the same. We can see in this slide there is this diagram. This diagram actually is the response. It's a step response of a system, and we can see this is our step. It has a value of 9, and we have this graph showing the practical response and the simulated response. Okay, so we can see that there is a lot of jittering here in the response we get from the experimental data, and that is typically will always happen in control system or electrical systems in general. Why? Because the data have a lot of noise, it has disturbance and so on, so you can get that smooth data. You can use filters to get better result. And the other graph is the other curve is the open loop response of the simulated system. So what we did is actually we took the practical response, which is this one, and we basically do the calculations the same thing, just like the first order system, but not using these equations, of course, using the second order system equations. We calculate the zeta, the damping factor, and the omega n, the natural frequency, and from that we calculate the transfer function and the gain and so on, and we end up with a model. And finally, when we run the check by giving the model and the system the same input, we end up with this graph, which you can say it's typically they are the same, but with a little bit noise, which is not going to make a lot of problem. So we can implement the same methodology for higher order systems, second order systems typically. Finally, there is several things we have to take in account. Those things actually when choosing the input signal to do a system identification, we have to make sure that the input of this signal is small and finite in amplitude, and we can simply say it's a bounded signal. So what do we mean by that is we also by doing that we make sure that the output will be stable, because it's a bounded signal. So if our system is internally stable, bounded input, bounded output. That's the first thing. The second thing is to avoid saturation, because using a large amplitude signals might cause saturation of the system, might put the system into danger, because we use the maybe high voltage or whatever the system we are dealing with. uh, Another point we have to take in account is when choosing the input signal is to make sure that our signal is rich in frequency spectrum. What does it that mean is actually we need to choose a signal that triggers all the elements in a plant or a system. So if we have a system that have several elements, some of them work in a specific frequency and the other work in a specific frequency. So if our input signal does not contain the frequency of all elements, we'll miss something in this system, right? So we will have the transfer function, but it will be inaccurate because some elements haven't been triggered. We had a slight difference between the experimental and the model. So what is the source of this error? Now the source is, first of all, nonlinearity in system behavior. System behavior is always going to be nonlinear in practical. Okay, there is no such thing as linear control systems in practical. The other one is the disturbance is actually a source of error. Disturbance in the system output, disturbance in the measurements, and so on will affect the model accuracy. Finally, we have model parameters change. Model parameters of course change according to different factors, like temperature. For example, if we have resistive elements and the temperature rise, of course we are going to consider that this resistor are going to change according to temperature, right? The same thing goes to a motor. When you have a motor and it starts heating, finally these are references that I recommend you read it so you will get a better idea. And if you have any question, please post it in the comments below, and take some time to follow me on Instagram at control_cs. Thank you.